All right, we're now live. This is day number 4 of the project. I'll just quickly recap, as I have been doing, where I am in the project, what I'm doing, what I'm going to be working on for the next couple of days. It's pretty straightforward stuff. Basically, we've taken the class, this 804 Quantum Physics 1 from MIT's OpenCourseWare, and we went through the first 10 lectures. There's 24 in total. They're each about an hour and 20 minutes, hour and a half long. We got through the first 10 lectures yesterday morning, and then now we're working through the problem sets. Now we start with problem set 1. Problem set 1 in particular has been taking a fair bit of time because it's not mostly based on stuff from this class. It's mostly based on stuff before quantum physics. So there is some stuff there that, is related to this class. There is some things that, we've done, but a lot of it is using formulas from classes that I didn't take, or using materials or concepts from 803, which is, again, the class that I didn't take. So it's been a little bit slow going for that reason, not to mention the fact that I haven't done problems like this in 8 years. So even just simple things like I was making some pretty dumb mistakes yesterday here, with just, simple algebraic mistakes. I was setting up a system of equation. I made them all equal to 0. There's no constants. And so, of course, it was degenerate. I didn't get anything. And I was struggling over it. And I was like, all right, I forgot to write the 1 over here. And that's why I'm having this problem. Or another one, I like trying to just do a little bit too much algebra in my head. I skip over, I forget a minus sign. So simple mistakes like that. There are some genuine conceptual difficulties I'm having here. It's hard to say how much of that is based on 803. Some of it could be based on 802. And again, it's just been so long that I'm not seeing the connection. But an example of that was the first question, the classical degeneration of the classical picture of the atom. Basically, why does the image of a proton and an electron orbiting it not work? And the reason is because an accelerating electric charge, which an orbiting object is always accelerating, would be just radiating light, and it would rapidly lose energy and fall down into the proton. Now, in this case, that equation, I'm sort of like, I know kind of the orbital velocity for gravity, but then I was thinking, well, yeah, but then you have this F equals ma, and so the mass is usually included, so I'm not sure whether I can use that equation just directly. I would have to figure out the mass term. So there's probably some stuff that I'm screwing up or I'm missing there. And so problem set 1 has been a little slow going. I'm hoping that 2 to 5, which we're going to be working on for the next probably today and tomorrow, I'm going to be working on 2 to 5. If they're really difficult, I might just push back my deadline of finishing all the lectures by the 15th and focus on really getting a grasp of this material, spend another extra day or so working on it, just because, you don't want to get too far ahead when you know that there's still these problems. And if I'm having difficulties just because of general rustiness in terms of these equations, these calculations, this kind of stuff, which is normal after, 8 years of not doing it, then I'm going to have to do that anyways. And so might as well do it now rather than get too far ahead of myself and then have to go through and really struggle through problem sets just for a week straight. So we'll see. We spent the whole afternoon. We had a little bit of a longer session. It was a little over 3 hours. And we still didn't get done problem set 1, which is not particularly fast. As I said, this is kind of near the difficulty level was kind of a little high. There was a few questions. One, for instance, was the double-slit interference, and I was trying to derive what the formula is, which was a little bit of a misguided attempt because I didn't actually know really what it was. And then I checked the answers, as you know, the formula is this, and I was like, all right, well, I didn't know the formula, so I'm trying to derive it, and I'm wasting a bunch of time. So today I'm going to try to, let's finish off problem set 1, or at least finish off a first pass of problem set 1. I think that given how much I've been checking the feedback, given this is something I want to go back to. I don't want to just leave it, with a bunch of questions that I had to check halfway. Oh, am I on the right path? This kind of thing. But we'll try to get a good coverage of everything. And then I'm going to say, move on to problem set 2. Let's try to do 2 to 5, try to go as far as we can in those. And then that will get us caught up with the lectures. So 2 to 5 will get us caught up with the lectures. Even though we're not done half of the lectures, this is half of the problem sets. I don't know what that means in terms of the material of the course. It could just be that the later material isn't covered as well in the problem sets as the early material is. Or it could mean that, you know, because there's a little bit of refreshing, relearning, bringing back old knowledge, that density was kind of a deliberate choice in the course designers. We also have midterms that have, I believe they have solutions, but if they don't, I'll have to double check. But we have some midterms. We can use as evaluation criteria. We have problem sets from other classes. There's lots of material. I don't think that there's going to be a problem with material this course. I was only able to get one final exam that had solutions, or one practice final exam that had solutions. So if we're doing this MIT challenge style, where at the end of this whole adventure, I'm going to test myself on an exam and then check the solutions, I don't have a lot of wiggle room there. So I am probably going to push that back as far as I can to make sure I'm as ready as possible, because obviously if I take it and then I realize, oh, whoa, I didn't actually know any of these things because I didn't study that well, or this kind of thing, it's going to really hurt. So let's go back into the problem sets. One problem I noticed I was having yesterday is that this problem set in particular references a lot of physical constants. It represents a lot of numerical constants that we're actually calculating. And I like to do things on the camera. I've been doing my best. I mean, it's a little hard because I've got the one camera here. I've got another one here for my notes, which you can see here. You know, so you can see my notes, which covers a very small window. You can see how big my hand is. So it's not like there's a lot of space here to show you guys and have it still be legible. So what I was doing is I was pulling out this textbook, this Ohanian physics textbook. I didn't mention this in the first class, but you can barely see it. This is a textbook I used for classical mechanics and electromagnetism. It's a big, thick book. You can see it's not. This is a heavy book, and I'm going there looking up things like Planck's constant and those numbers in this book. Whereas really I should be Googling it. That would be much faster. I'm not. It's going to take a lot less time than me flipping through pages and then realizing it's not in the form I want, or they don't call it that. They call it Coulomb's law. They're not calling it Coulomb force, so I can't look up Coulomb force. So given that that's causing a little difficulties, what I've tried to do is make my windows here so that I can do the problem sets through the browser, but it'll also be on the browser. So if I have to switch over to do some calculations or to do some other things like that, it'll be relatively easy. I've been kind of blowing through the numerical calculations and just trying to do order of magnitude ones, because, you know, working with I don't have a calculator at hand right now, and working with my phone calculator, the computer calculator, with all these, you know, scientific notations is 10 to the power negative 27, and then we got to take the, you know, square root of that and this kind of thing. It was just a little tedious, and I was making a few calculation errors, so I kind of switched to, you know what, let's not try to get the exact answer, let's try to get the right order of magnitude, so focusing on powers of 10, and, you know, when you times 6 times 2, you just bump it up a power, that kind of thing. And that was going fairly well. To be honest, MIT classes that I remember don't do a lot of numerical calculations. It's largely pencil paper. Most of the classes I did in the MIT Challenge did not use the calculator at all. I know that's a little less for physics, but definitely the math classes. But even a lot of the physics classes, it was, you know, for function A, B, and C, find the relationship of A, B, and C. But, you know, normally in A, B, and C are actual numbers, but here we're not using numbers, we're using A, B, and C. And so in some ways that's a little better, because you get kind of a generic way of solving the problem rather than just like ballparking it based on numbers. So I'm going to jump back to the problem sets right now, and let me get the window ready, and we can get going. So we finished here, problem set 4B, and I was, let me just refresh where I got with the problem, but let me just reread it. So in an experiment performed by Janssen in 1961, electrons were accelerated through a 50 kilovolt potential towards 2 slits separated by a distance of 2 times 10 to the negative 4 centimeters, and then detected on a screen 35 centimeters beyond the slits. Calculate the electrons' de Broglie wavelength lambda and the fringe spacing omega. So we know from this kilovolts is going to be the kinetic energy that it gets accelerated over. And we know that, where are we here? We have lambda is equal to this h Planck's constant over the momentum. And where are we here? We know the fringe spacing is related to it this way, lambda big D, which is the distance. So if we have the spacing here, this is D, and where this is D, this big one here. So D over D lambda is going to be equal to this fringe spacing. So we just need to figure out how fast the electron was going. And then from that we can compute its momentum, and from that we can compute its wavelength. And then from that we can also compute the fringe spacing by just this formula, which was derived basically in part 8. So 50 kilovolts of the electron is equal to the kinetic energy. So we have 50 kilovolts. Do I need to have anything for kilovolt potential? Hold on a sec. Let me just check here. I have to double check these things. Yeah, joule per coulomb. So this is 50 kilovolts. So it's equal to energy divided by electron charge. So if we have energy divided by charge, we need to do, this is going to be 50 times 10 to the 3 volts divided by Q electron is equal to 1/2 mass electron B squared. So we just times everything by 2. And then because this is 100, we can just go 1 times 10 to the 5. Get rid of this, divide out the mass, and then take the square root. And this will be, our velocity is going to be equal to 10 to the 5th divided by mass of the electron, charge of the electron. So let's look that up. All right. Google is your friend. All right, so let's just do this here. 10 to the 5th. Mass of the electron is 9.11 times 10 to the negative 31 kilograms. And then this is going to be 1.6 times 10 to the negative 19th coulomb. We did say kilovolts, right? It wasn't electron volts, kiloelectron volts. Yeah, kilovolts. Okay. And so then all that is required to do is to calculate this right here. So it's going very fast. I think this is what the idea here of this is. So we will just, I'm going to just say this is 10, take off an order of 1. 1.6, I mean, we'll just kind of say that's 1 for right now. I'm doing an order of magnitude calculation because I don't want to calculate all these numbers. So we're going to have 10 to the 4th, and then this is 10 to the negative 31 and 10 to the negative 19. So this is 10 to the negative 4150 square root of 10 to the 54, which is equal to is equal to 10 to the 27th. So velocity right here, and I'm wondering, this is way too fast right now. I made a mistake somewhere. I don't think I can calculate this because this is going to be, obviously this is way too fast. We're going to have relativistic problems here for doing it. So this is not the way to calculate this then. All right, that was my first guess at how to do this. Let's think about this a little more. Can we do it with just directly the kilovolts without having to go through this using these constants of electron mass and electron velocity? This is energy divided by charge. So I think what I need to do here is we just know that, is there another relationship with mass and wondering whether I can get this lambda without having to do that way of doing it, because we're going to have problems if I'm not doing it relativistically at that point. So 50 kilovolt potential. So that's the energy. Do we have, I think we can do it because we're assuming that the energy is related to, now let me go back to my notes. The energy is related to the momentum. Now let's get the de Broglie. And then maybe we can avoid that. So let's just get, where did I write the de Broglie wavelength? Okay, so this de Broglie relation, we can do H is proportional, or E is proportional to this H bar omega. Let's have this here. And the, so if we, omega is the, or is equal to lambda frequency, because that V is the, no, that mu I think is the actual frequency. So it would be not lambda. Frequency, that's the inverse of that. So this is equal to H times frequency. I don't know whether this is, so this is maybe a conceptual issue for me as well, is that I'm not confident right now that I can ignore the fact that the difference between a photon and an electron is that it has mass. I know the way we were doing this is that the energy is related by this, this function here, but a photon obviously is massless, so the momentum of a photon is maybe different from something that, you know, has this thing. So I'm going to just do it with this formula and then see if that's right. But it would mean that I don't need to worry about mass if I'm using this formula. So, so let's work it this way. So we have the energy minus the electric charge. So if I want to get the energy, I have to times 50 kilovolt times 50 times 10 to the third volts times, sorry, this is volts. This is volts, which is joules over Coulomb. And then this is going to be times by Q electron. And this is the energy is going to be equal to this Planck's constant times the frequency. All right. And so if I just take, but I don't know whether I can get the wavelength without a speed factor. So maybe that's why I can't. So I can find this frequency is equal to 50 times 10 to the third Q electron divided by H. But I don't know whether I can get the wavelength there from that. And that's what I need for this question. I'm just going to move this here. Oh. How did this get separated? Hold on a second. All right. Let me just adjust this way. Yeah, so the question is, how do we get the wavelength? And I tried to do it with just a kinetic energy formula, but that seemed to be speeds that are faster than the speed of light. Because they're faster than the speed of light, we're going to have issues with relativity. So that made me think that that's not the way to do that, that I'm going to be using the kinetic energy just directly. So I use this de Broglie relation here with this formula here. But now I'm sort of stuck on the same problem that I can get the frequency, but to know the wavelength, I need to know how fast it's going. So I still need to know the speed term, the velocity. There's something I'm missing here, but I'm not sure what it is. Well, you know what? I think I'm gonna just dig into the solution right now and just answer my question, because otherwise we might be here for a while. So let's open the file here. Where are we here? It's question 4. Okay. B, to calculate the electron's de Broglie wavelength, we need to use the de Broglie relation. Lambda is equal to h over momentum, and we must know the momenta of the electrons. The electrons begin at rest and are accelerated by a voltage of 50 kilovolts, acquiring some kinetic energy. P squared over 2m is equal to Q change in voltage. So did I just do the formula wrong here? So let's just try this again here. Now that we have a little bit of a hint, let's just try this again. I'm just going to scroll this up so I'm not looking too much at it. So what did I say? I said that the voltage divided by the charge is equal to the kinetic energy. And then that was 50. I'll use their notation so I can. So this is delta V over Q is equal to 1/2 mv squared, which is equal to 1/2 mass of the electron. I'll sort of E here, sub E, V squared. So this was 2 delta V mQe is equal to V squared. I have that. And what do we have? We have momentum. So momentum is equal to Vm, right? I'm not making something really elementary mistake, am I? Momentum squared divided by the mass. Let me just look at this again. I have delta V. What did I write? Delta V square root of delta V 2 delta V m Q. And they're saying this is velocity. So if I times by a mass term here and a mass term here, then we go from minus a half term on the outside here. It should just bring it up here. No. Mass squared, no. No. Let's see, what am I doing here? It's equal to 2 delta V m Q minus 1 1/2 is equal to root 2 delta V 1/2 minus 1/2 Q minus 1/2. This is V, and then we add the m to it. M to the 1. This should cancel over, so we have momentum is equal to square root of 2 delta V m over Q. And what do they have? That this Q is in the wrong place here. I think I must be doing something wrong. Voltage, Q voltage. Let me look at volts here. Voltage is in joules. joules per coulomb. It is joules per coulomb, right? Voltage is. Potential energy divided by charge. So why is this appearing as a, why is it up here and not here? Oops. Why is it appearing up there and not there? Shouldn't we have, if it's 50 kilovolts, so this formula makes sense if we were multiplying them, but oh, of course, because I'm doing joules divided by C, so I need to have a factor of C up here. I'm just rewriting it. Okay. All right. Just me doing algebra wrong. All right. So we've got this formula here. So let's just get this right now. Equal to square root of 2 times 50 times 10 to the third. And then this is not underneath. It is up top. Electron mass, which I should really keep track of all of our. I think it's times 10 to the negative 31. Yeah, 9.1 times 10 to the negative 31 times electron charge is 1.6. 10 to the negative 19 equal to square root of, so this 2 times 50, so we have 10 to the 5th. This is going to be, I'm just going to say 10 to the negative 31. And this I'm just going to say is, that's 1.5, so 10 to the negative 19. So we add these up, all these terms, and we have minus 5. This is going to be 14. 14 plus 31 is 41, 45. So this is going to be square root of that is 10 to the let me just do that again. 19 plus this is 40, 50, 45. 45 divided by 2 is going to be 22.5. So square root of 10, I mean, that's like 3. So it's like 3 times 10 to the 22nd, roughly. Okay, so this should get us momentum of that. Oh, de Broglie wavelength. Let's just calculate that directly. So the de Broglie wavelength is going to be equal to, is it h over p? Yeah. So h, let me just get Planck's constant. I think it's, see if I can remember Planck's constant. Planck's constant is, no, Planck's constant. Yeah, 6.62. 10 to the negative 34 divided by 3 times 10 to the 22 this is going to be equal to sorry, negative 22. Negative 22 is going to be equal to approximately 10 to the 22 off of that is 10 to the negative 12. 10 to the negative 12 meters, I believe. And so if we go back to the original problem, so the fringe spacing is equal to d over d times lambda. Correct, it's that way. Yeah. So that's 0.35 meters divided by 2 times, what is it? 10 to the 4 centimeters. So that's 10 to the negative 6 times approximately 10 to the negative 12. So we just take a factor of 6, multiply this by 6. Am I right there? This is too small. Am I dropping a factor somewhere? It seems too small. These are millimeters apart. This is on the order of magnitude of 10 to the negative 6, 10 to the negative 7. Let's just see what the answer is, see if I'm wrong there. Okay, yeah, 10 to the negative 12. Oh yeah, 9.6 times, yeah, 10 to the negative, I said around 10 to the negative 6, 10 to the negative 7. So I was right there, but that seems very close together, no? These are like, what is this? Like micrometer. This is the interference pattern, and you're going to need a microscope for this. So let's go back to the problem set. What values of d, d, and omega, what would values if they were simply scaled up for use of visible light rather than electrons? So let me just write C here. So, simply scaled up for the use of the visible light. So what are they trying to say? Are we trying to maintain the fringe spacing, or? I mean, if we have visible light, it would be wavelength, like the wavelength of visible light is, we said already, is between 400 nanometers and like 700 nanometers. So this is equal to what? Like nanometer is 10 to the negative 9. So let's say this is just like 0.5. Add 100 to this is times 10 to the negative 7. So we got 10 to the negative 7. I mean, I guess we want on order of, what is this, micrometers? The fringe spacing? I mean, that seems really close together to me. Like you'd think you'd want it more spread out if you're doing an experiment. All right. So let's, if we had this, then that means that 10 to the negative 7, this is 10 to the negative, so we're 5 orders of magnitude smaller, the electron. So if we wanted it this way, 5 orders of magnitude smaller. See, I don't understand what it's simply scaled up for use with visible light. As if we're saying is scaled up for visible light, am I assuming that like just everything is increasing by this factor of what? Of like 4 or 5 orders of magnitude? Do I want to do it that way? That seems wrong. All right, let's just guess that and then see what they actually want. So if we increased everything by let's say 4 orders of magnitude, what would we have? We would have so times 1,000, so 0.35 times 10,000. That seems way too big. 35 meters, 3,500 meters, and then this seems wrong. D is what, 2 times 10 to the negative 4, and then we scale it up 4, so it's like 2 centimeter slits, and then this is equal to what? Lambda is going to be what, this 10 to the negative, yeah, let's say 10 to the negative 6, around there. This is, oh, what am I doing here? 15, no, not 15. 1750, 1.75 times. So we're having 3 there. Moving it from there. It's going to be 10 to the negative 4. This, I don't know. This question doesn't make sense to me. What do they want here? Between the wavelength and de Broglie limit is 100,000. Okay, so I said 5 orders of magnitude, but it's 6. Suitable values are then 20 centimeters, 35,000, 35 kilometers, and then 9.6 centimeters. So I'm off by 1 order of magnitude here. I must have missed something. 550. There's 3. Oh, because it's 550. 9, 3. Yeah, I must just have added 1 less when I was rounding it. All right. Okay, so let's go on to number 5 now. Oh, we finished one section. I'm gonna have to buy more books. I'm gonna go through this material too fast. All right, let's go forward now. Problem set 5, electron diffraction. Watch the video on matter waves. Oh yeah, this was the one. This is a long video. I don't know whether I want to watch this whole video right now. I'm going to skip 5. It's just because this video, I checked it last time when we were going through the problem set. It's like an hour long, and I don't want to go through that right now. All right, let's do 6, single slit, diffraction, and uncertainty. Visible light light with a wavelength lambda is incident from a distant source onto a single slit of width delta x. Denote the propagation direction as z. Direction transfers is x. Assume the slit is a few times larger than the wavelength. Okay, this is, again, this diffraction stuff, I feel like it was covered in 803, so I'm struggling here because I didn't take those classes. So we'll work on it a bit, but I'm going to jump to the answers a little sooner than later because I've been banging my head a little bit because I've been lacking some of the formulas. I mean, some cases I've just been making mistakes, like I was screwing up stuff just right earlier because I taking voltage joules over coulombs, and I'm dividing coulombs again, so I've got over coulombs squared. So I can't blame all of it on not having taken the class, but there's definitely a component of it in this problem set. Estimate the width W of the pattern observed on the screen that is distance D much farther than lambda away. Yeesh, okay. So we've got, this is the setup. I'll just draw it up here because we're skipping over 5. So this right here is this dx. This right here is d, and we know that d is much greater than lambda. And then we have some kind of I don't know, this kind of thing going on, I guess. And then we want to know that there's going to be some kind of accumulation of the photons at the end based on going through this slit. By assuming that the slit acts as a collection of emitters all oscillating in phase. So the way we're going to solve this problem, I guess, is that each of these is imagined to be some kind of point source. So we're going to have to integrate over a bunch of things as they're each accumulating into this wave that is hitting. So if we assume that this is really far away, then I guess what's happening there is we're not having to worry about, like if it were right here, for instance, maybe it doesn't have time to like average out. So can we treat this as this is like a multi-slit problem that we're integrating over. Oh, Timothy's asking, what point do you start feeling like you understand quantum physics? Well, not now, but I'm not even doing quantum physics here. This is just regular physics. So I will let you know when I do. All right. You know, I don't know whether I can solve this. I don't know how much I want to just like struggle against this right now because this is not, again, this is not something that we covered in the lectures. I know for like, let's just start just on some assumptions. Let's not try to solve the whole problem because I think working it out analytically is going to be too difficult for me. But we know there's going to be an integral. So I know there's going to be some integral because we're integrating over each of these emitters that's giving off things. And I think, do I treat them each like double slits that are interfering with each other? Do I need a double integral for that? Is the idea that I can like take points, let's say A and point B, as if they are in some kind of like as if these are two double slits, and then we just have to integrate over it twice of all the interference terms. This is just speculation. I just want to see whether conceptually I'm on the right track or whether there was a completely different way of looking at this problem. So what was the formula for the interference pattern here? Well, I mean, the width is characterized by this omega, which was d over d, this here. And so if we were to say that, yeah, at a very high level, my imagination is that this is an analog of the single slit or the double slit, where you consider each point in the slit, you integrate across and you do each one. I mean, that's my best guess right now. You know, I'm going to just move on to the answers here because I don't think it's going to be forthcoming unless I go back to previous classes. So let's get the starting point. I like to do this sometimes too. I like to, you know, if you're looking at a solution, don't look at the whole solution. Look at just enough of the solution to get yourself going again and see if you can solve it, because otherwise you're just kind of wasting it. So let's see if once they throw some equations down, I can get it. We're just going to skip over this. We didn't do 5 because I didn't want to watch that long video, or at least not right now. We could do 5 later. From the diagram, one sees that the pattern of the screen is a destructive minimum at the angle where each emitter can be paired up exactly with one other emitter, such that the path difference between the waves emanating from them is exactly pi over 2. From the geometry of the diagram, this is equivalent to saying, ooh, okay. So I'm sort of right. I know that there was going to be an integration here, but let's start with this, see if this gives me anything that I can go off of. So I think the idea here is that we're considering let's say two hypothetical emitters at x0 and x1. And these are emitting their kind of, the destructive angle is exactly pi by 2. Okay, because we know that the constructive angle is pi because of the fringe spacing. So, excuse me. Sorry, it's allergy season. I'm feeling it a little bit today. All right, so so these are going to has a destructive minimum at an angle where each emitter can be paired up with exactly one other emitter, such that the path difference between the waves emanating from them is exactly. So if we went from our last formula, I wish I had the diagram here for this. All right. So if we went from the last case where we have this sort of this interference pattern, this corresponded to, what was it, d sine theta m's m I think the m is just the number, no? Yeah. So this first node is d sine theta is equal to this. So each one has to be paired up with that. So we have, all right, delta x divided by 2. Why is this divided by 2? Why is that divided by 2? Because in the original one, if we go back, it was, if we go back, it was just d sine theta. Why is it divided by 2 in both places? Wouldn't it just have 1 divided by 2? I guess what they're saying is that this is going to be divided by 2. This is my theory, at least. This is going to be divided by 2 because you need to be able to pair it up with one other one. So you can do that here, and you can do that. Like you can do that when it's this the distance is exactly half because it has to be paired up with half. So that's why we get the factor 2, because we have x0 here and x1. So this distance has exactly one other emitter that is going to hit off of. For instance, this one here and this one here is going to have exactly one emitter that it's going to hit off of. Whereas if these two had been, if they had been less, if this had been like divided by 3, we'd have 3. If it had been, you know, more than 2, so if this had just been 1, you only have 1 emitter, so it can't interfere with itself. So I think that's what's happening here. So this basic idea here, we get equals lambda over dx. How are we getting rid of this sign here? Like we just dropped the sign term. We just get theta. I mean, are we assuming that, like, what is the assumption here for small angles that theta is equal to, like, is the idea that for small theta, which it would be the case if d was much greater than this, that sine theta is equal to theta? Is that, like, it's approximately equal to theta? Is that the idea? I don't know whether that's not being stated explicitly, which I don't really like. Okay, let's go forward. Oh, yeah. Next sentence. Where in the last step we invoked the small angle approximation. Sine theta is roughly theta. Since tan theta edge is equal to... So I need to construct this diagram because I don't really have this diagram constructed. I don't know whether did they construct the diagram in this one? I don't think so. No. So hold on a sec. Where are we here? This is question 5. Okay, I don't want to skip too far ahead. Okay, so let's try to construct this thing. We've got enough pieces of the puzzle now to try to construct what's the diagram they're trying to talk about here. All right. So obviously this is not to scale. Excuse me. So let's get the destructive pattern here. So this is our theta. And we're saying that, what is it, tan theta equals this. So tan is opposite over adjacent. So we have, this is sine theta. Where's the d? D is this. I think I've got the triangle wrong. That's what I've been screwing up. I think I got the triangle backwards. I think that what we're trying to say is that it's like this. No? And this is theta. And this is d. And because we have 2 points in here, this is this delta divided by 2. This is theta. And this is, I guess, our first. So what was the first formula? It was d sine theta is equal to lambda over 2. This was the original formula for our diagram. So our sine is this over this. But how do you get lambda out of this? What's the triangle here? Like, I mean, this can't be the thing we're considering. So let's just figure out the trigonometry just based off of not what I think it would be, but off of what we've actually been provided, so we can construct this triangle. So we have this divided by 2. So if sine of whatever angle is going to be opposite over the hypotenuse. So what is the opposite? Well, if this is over here, then that must mean that this was the hypotenuse. No. Like it was equals. So if this, what's the triangle here if this is the hypotenuse? I'm not sure I understand this. I need to see a diagram for this. Let's see if my book here has anything on single and double slit diffraction, because I think I just need an explanation here. I don't really want to move on. Diffraction is, here we go, diffraction. This is related to the quantum physics stuff, so it's not just some kind of little classical exercise here. All right. So we're taking a little reading break here. I'm going to switch over to displaying the full camera, just because otherwise it's going to make things a little bit harder to read here. And hopefully I can do this without bumping things. I can just move my microphone just a little bit there, so we have a little bit more space. All right. Diffraction by a single slit. Okay, this is exactly what we've got right here in our example here, was this diagram where we have all these points. So let's just start reading. Pretend that each point in the front reaching the slit can be regarded as a point source of light emanating a spherical wave. The net wave in the region beyond the slit is simply a superposition of all these waves. Finding the position of the maximum minima in the diffraction pattern of the slit. Figure 40.3 shows that some rays associated with the waves spread out from the points of the wave in front of the slit. All the rays lead to a point P. Oh. Okay, here's the diagram. Here's the thing I'm trying to construct, and I'm not getting. All right, so let's draw this. See if we can't solve it, because I'm trying to do this thing over here. So let me draw it. Let me draw it like this and copy it over and see if that doesn't clear up some misunderstandings. So. Two-point P. Oh, okay. So these are all aimed at a particular point on the. So let me just redraw this so that that's a little bit more clear, because these are not actually parallel lines. These are all pointing towards a particular point. So let me accentuate that a little bit more. Okay. So this right there is theta. This right there is obviously sine theta. this is our d divided by 2. So this is d divided by 2 sine theta. And d divided by 2 sine theta. So when basically what this is saying is that each of these we're considering each of these like lines to a particular point, and this will be a destructive point. And I'm going to just call this line is going to be, I'm just going to call it, let's call it K. This is going to be K prime when K minus K prime is equal to lambda divided by 2. So when this one is a half phase out a step, it's going to be destructive, and when they are in phase, it is going to be constructive. And this is the trigonometry that I'm supposed to do, and this is why you do this calculation. All right, so let's go back and see if we can solve the formula with this little set. I'm going to put a little bookmark here. Do I have a little piece of paper I can put as a bookmark? You know, I'm just going to dog-ear the page right now, so that we can jump back to this easily if we want to continue looking at the diffraction stuff. Because I feel like now that I have this diagram, I actually know what they're talking about doing the diagram. So let's go back to our problem set. So what are they saying? They're saying that this is going to be from the single diffraction experiment, that this d sine theta over 2, hold on a sec, I got a 2 here, and we're using the small angle approximation. This now, what is this, tan theta edge is equal to so why is this tan theta over WD? So it's d divided by 2. So the difference between these. So hold on a second. Let me see if I can draw it a little better. New piece of paper here. You know, definitely need a new notebook. I'm drawing a lot of diagrams. So we've got so this is our first point, and then our second point is going to be here. So this is our diffraction spacing. And the idea being that this is equal to lambda divided by 2 for destructive. And this one here, we have to do same thing, except there's not that much difference between them. So it's going to be more like this. That probably doesn't actually work. Maybe I should redraw it so that it's more physically plausible. This eraser has not been super helpful. It's been making a big mess. I have to take the vacuum here after and clean up all these eraser bits. So let's try to make this more physical. So again, we've got these two here, and then let's just make them should be kind of evenly spaced off to here. So let's draw it. Oh, help if I can draw a straight line. All right, and so in this case, this is lambda over 2. And in this one here, where are we here? This one here is going to be the shorter one, so this one here is going to be lambda over 2. And this is omega. So what is the triangle here that is defining? I guess it's between the 2 points, right? So this is W. And this is roughly D. But there's no, where's the right angle here? I guess because, oops, that worked. This is D, tan theta. This theta is here. Oh, I guess because this is a right angle. No. There's probably some trigonometry that gets this theta over to this theta now. Is there an explanation of that? Let's go back to our book. I assumed it would be more obvious. All right, do we see any tangencies here? All right, this is still not entirely forthcoming, so let's keep going. Oh, we've got a nice diagram here. Oh, that'll be helpful. I should have skipped ahead a little bit. So by this kind of, I'm going to switch to my pen here. I haven't been as consistent as I would have liked. I was hoping that when I was jotting stuff down from there, I was going to put it in pens so I would know what was my work versus their work. But I've been kind of going back and forth too fast. So I haven't been doing that consistently. So we have this omega is equal to lambda. Is it omega? I think that's just W. Width over dx. D. Oh, okay. So this is how we're getting at it. I didn't draw it as well as I should have. So if we draw it like this, and we have this way, this way, then how does this add up to? This adds up to, because this is going to be 90 minus theta, and then this theta. Okay, right. So for basic trigonometry, this is going to be our tan. So it's going to be this straight line. And then this is D. Oh, okay. So, and we're doing two small angle approximations with tan and theta. With those two small angle approximations. So what was the question again? Let's go back where we were with the question. Estimate the width of the pattern. So the width of the pattern is equal to this. As the width of the pattern. All right. So I'll just highlight the answer here. Okay, so this was a challenging one, but I feel like I understand it now. So, you know, a good way of doing these things as well is that, you know, obviously just looking at the solution, you get the right answer, but that's not the same as solving it yourself. Now, in this case, I can't necessarily practice on a different question or a question that's phrased differently, and there's always a risk that you've memorized a particular way to solve a problem rather than a deeper understanding. But I can save this, do this question again later without looking at the book, and see if I retain the insight or the intuition of the single slit experiment. So let's go back here. We're now in B. So B, in the photon picture of light, the light beam after the slit comprises a large number of photons with a range of values of transverse momentum. Due to this range of propagation speeds in the x direction, different photons hit the screen at different spots. Using the knowledge of W, estimate the range of transverse values of momentum, assuming that dpx is much, much less than p, where p is the photon momentum. So again, let's try to draw a picture. So what do we have? We have, again, the slit. We have the photon, which is going to go strike at the thing here. And it's a vector, so it has two components. It has momentum, and let's say it has momentum z. I'll just draw a little vector here. And then I guess they're using, I'll just call this dpz, and this is dpx. So we need an estimate of that. Range of transverse values of momentum, this. So I think are we looking for like an order of what is the momentum in this direction if it's that way? So if it travels, so we know that it travels, you know, it's traveling at the speed of light. So how do I want to do this? Excuse me. So this is D, and this is this. And we know that it was traveling at the speed of light. How do we get the momentum from that component? Or what would be the best way to get the momentum from that component? So we have the distance. Let's call this dt, d sub t. So d sub t is equal to square root of d squared plus this squared. And this is how far we went. Is there a different way of getting it so I can get the momentum so I'm not getting the velocities here and then? There must have been some momentum in this direction, some momentum in that direction, right? I don't know if there depends on D. Does D? Oh no, D is here, so it has to depend on D. So this is the distance is going that way, but we want the momentum that's going that way. So we need some kind of overall proportionality. So we want distance proportionality, I think, is going to be the momentum proportionality, no? So we have dpx divided by dp is equal to dpx divided by all this. And so I'm just going to call this, what do I want to call this? Just call this A. A is equal to, and we know that this is the width. So we have width is equal to lambda over dx d square root of d squared plus lambda squared dx squared d squared equal to, that's out. So these will sub out a factor of d, so it's going to be d, and then we're going to cancel the d's. This. I'm not wrong here. And then we're going to have what? We're going to have 1 plus So I don't know whether there's something else I want to do here. Oh, can't see my work here. Let's look at the answer. Will be those at the edge of the pattern. For such a photon, what is the greatest transverse momentum will be those at the edge of the pattern. For such photons, their travel direction is given by theta equals bpx over p. The theta equals roughly w over d. So I tried to calculate this, and that was my mistake. So theta is equal to over p all right, which combines with theta equals approximately w d to give okay. I'm not sure I understood that completely. C. Since we know that each of the photons went through the slit, we have effectively measured the x position of the photons at that point. Experimental uncertainty associated with this particular measurement is dx. Since the momentum of the photons in the transverse direction is conserved between the time they go through the slit and the time they hit the screen, effectively also measure the uncertainty in their transverse momentum values. Since the momentum of the photons in the transverse direction is conserved between the time they go through the slit and the time they hit the screen, uncertainty, the transverse momentum. All right. So E is equal to, let's just write C here. E is equal to, says, HC over lambda. And we have E is equal to momentum C. So we have C's cancel. So we want to show that the dx, what was our what was it we have? Dx is equal to, from the last one, and then we have width is equal to lambda lambda over xd over d. The d's cancel. This p. To get photon momentum. We have this px. This is equal to lambda p, but p is equal to h bar over lambda. So we cancel the lambdas and we get h. Okay. Heuristic realization and uncertainty relation which lies out of quantum mechanics. We derive the number in increasing general ways. Okay. So problem set 1. I'm going to just make some notes here so I don't forget what I struggled with, what went well. Because just looking at this scratches, a week from now, 2 weeks from now, I'm probably not going to be able to recall what were the issues, what did I get right, what did I have to look up, this kind of thing. So I'm going to try to write all of that down so that if I go back at this, I know what gaps need to be filled and I know what things might be missing and that kind of thing. So let's look at it. Question 1. I'm going to just put this was unfinished and unchecked. Problem, I don't know. To get stable circular orbital velocity for electron. Q2. Which one was Q2? Q2 was, oh, right. Q2 was dimensional analysis. So, finished. I'm going to put needed help. So I didn't get it right away. So dimensional analysis, what do we have here? We have problem, sloppy math, 2, didn't try system of linear equations. So that was a kind of methodological thing that I think I would apply from now on. Mistook energy units. Note, need to practice / memorize DIMS for basic constants and expressions. So I need to be able to convert things back and forth between different expressions here. So let's go on to question 3. Q3. How did that one go? Well, what was Q3? Q3 was 1, 2 is a long one. 3, yeah, 3 I basically got right, but I didn't calculate it. 3, what was this? Wave photons. Order of magnitude guesses rather than calculate exactly. So that's something to watch out for. And then 4 was, okay, 4. Q4, double slit. Didn't know, needed to look up. Understand now, not super well. Q5, didn't do yet. Long video. Q6. Q6 was single slit. Didn't know. Had to look up. Hard. Okay. So that's going to be my problem set 1 review notes, just in case I want to come back to this. I think I'm probably going to just decide how relevant a lot of this is for the quantum mechanics stuff. I might come back through and do some findings. I don't know whether I'm going to redo all the problem sets. We'll just sort of see. So let's close these out right now, and let's open up problem set 2. We're making progress. All right, question 1. What is the difference between phase velocity and group velocity? How do they differ in gravity waves in the open ocean? So this is, yeah, this is 803 right here. All right, definitely 803. So phase velocity and group velocity. What I'm going to do is I'm going to give a guess, and then I'm going to look it up in the book, and then we're going to see if we change our answer. So my understanding is that we have a wave this is V group, and this is V phase. That is my guess. And so for waves in the ocean, the phase velocity is different from the group velocity in that phase velocity is how quickly it's going up and down. Let's go write that down. And then the group velocity is how fast it is moving ashore. So let's get out our Ohanian. Let's see if we don't have anything on waves. Do we have anything on waves here? Waves is page 412. Let's just switch over here a sec temporarily. Let's just switch over to this view. Okay. Do we have anything for phase and group velocity? Oh, here we go. So let's read it out. So let's just jump. The lack of dependence on speed on shape is a rather special feature of waves on a string. For many other kind of waves, the speed does depend on the shape. So different parts of a wave pulse travel at different speeds. Consequently, the wave pulse changes shape as some of its parts get ahead or fall behind other parts. Because of this, the wave pulse tends to spread out or become more shallow. A medium that gives rise to such behavior is called a dispersive medium. In contrast to the case of a harmonic wave in a string, harmonic wave in a dispersive medium cannot be regarded as simply succession of wave pulses because the pulses change their shape, whereas a harmonic wave does not. There is then no simple connection to the speed of a wave pulse and the speed of a harmonic wave. To distinguish these speeds, we call the speed of the peak of a wave pulse the group velocity, and the speed of the harmonic wave the phase velocity. The group velocity is sometimes called the signal velocity because it describes the propagation of signals in the medium. If we want to send a signal by means of a wave, we must use a wave pulse rather than a harmonic wave. The latter has no beginning and no end, lasts forever, and therefore is useless as a signal. The phase velocity of harmonic waves in a dispersive medium depends on wavelength. For instance, ocean waves of a long wavelength have a higher velocity than those of a short wavelength. Discuss this characteristic of ocean waves. So I think I got the question right. You know, let's put another dog ear in my Ohanian here so that I can come back to this if I need to. And let's see if I got the right answer. I think doing tight feedback cycles at this stage is being helpful because it's going to save me a lot of headaches later. If I get some feedback. I do like to test myself on the problems, really push myself as much as I can, but at the same time, waiting too long to get feedback, struggling on something when you could get the answer, does somewhat frustrate the learning process. So let's go over here now and look at the solution. So let's open that up. Oh, hold on a sec. I've got to open a new window. Oh, let me just zoom in here so we don't. Hopefully this won't cause problems for you at home. It's a little bit cropped down. All right, hold on a sec. All right, I will adjust it for right now. Okay. So given a dispersion relation, omega k, the phase velocity is defined as v equals omega over k, and the rate at which a single plane wave, single k mode, moves within a wave packet. The group velocity is on hand defined as vg equals the derivative of the wave with respect to k, and is the rate at which the envelope or pattern of wave packets move. Note both are generally functions of k. So I missed here. I'm going to write this down because this is very clearly 803 stuff. It's Okay. So we have velocity phase is defined as over k, and velocity group is defined as delta wave over the derivative with respect to k of w. All right, let's go back to this problem. I think we can zoom in a little bit more here. Does this make sense? Let me just. How does this look? Okay, I think you can see it. So, all right. We got the general idea, but obviously not the formula because we didn't study that. I'll have to see. I'm not sure whether this Ohanian book necessarily has the stuff from 803. So we might have it in this quantum physics textbook, but we might be missing some of those things. So I'll have to see what I'm going to do if I need to learn some of it. B, why do waves break on a beach? Waves seem to get taller as they approach a beach. Is this accurate or an optical illusion? Again, this is an 803 intuition, but let's try to think it out. Why do they break on a beach? Well, I actually don't know. Waves seem to get taller as they approach the beach. So it has something to do with the phase velocity and group velocity. And we just read in the book that because of the dispersal mechanism in water, sharper waves move faster. So it's probably because of this dispersal mechanism that we have, because a given ocean wave is kind of superimposed with various kind of wave things. As it gets to the edge of the beach, these ones are moving faster, and they're kind of adding up in the end, which is what is causing it to break. And then they seem to get taller. I would say yes as well, because they're going to constructively interfere. So I'm going to say because for smaller lambda, waves are faster, thus they accumulate and break, I guess. And then I would say it is not an optical illusion. Let's see if that's right. I think we can. For gravity waves, the dispersion relation is given by this. The ocean is deep, so KD equals infinity. Tan KD is equal to 1. This means square root of kg, so in deep water, the phase velocity is thus twice as quick as the group velocity. All right, from the dispersion relation, equation 3, we see that as waves, I'm going to write that down here. I think this is 1 over, no? That's the only way that makes sense to me. Yeah, it's got to be. So if you've got 1 over this, you... kg. All right. This is probably square root, actually, now that I think about it, because if we've got this equal to 1, then this is square root. So that's what is being cropped out in this PDF. All right, for the dispersion relation, furthermore, as one approaches the beach as d gets small, so that tan h hyperbolic tan of kd is equal to roughly kd, this omega is equal to k square d. This gets smaller as d gets smaller. Put this all together, we see that the front of the envelope of the wave bracket slows down as the individual plane waves farther behind continue to move forward at a fairly quick rate. In other words, the difference between VF and VG, see what's VF? VF and VG changes. This causes the waves to scrunch up at the front of the envelope, so the height of the waves increases, since the total volume of water must remain constant. So the fact that waves get taller is not just an illusion. Eventually, the heights of the waves increase to such a point that nonlinearities set in and the waves break. To get a feel for the distinction between phase and group velocities, check out this. All right, let's check it out. Oops. I'm going to open it in a new tab so that I don't run these. Oh, look here, guys. We can see phase and group velocities. So phase velocity is 1. Set group velocity here. So what if we have, so higher phase if at 0.5. So you can see here when we have faster phase than group velocity, the waves move more quickly than the overall packet. Can we do the opposite? Yeah. So this is kind of cool. Oh. All right, so that's kind of an intuition, visual intuition of what's happening. All right, let's go back to here. Let's go back to our problem set. So, C, the surfer is waiting for a wave packet of ocean waves, which is approaching a beach. From concrete list, let it be an infinite linear beach with beautiful beige sand, constant slope, warm air, little surf shacks, and Fiji bars every few kilometers. To the surfer's frustration, the first few waves appear to dissolve before arriving. Is this accurate or an illusion? Use the difference between wave and group velocity, phase and group velocity, explained by big waves tend to approach the beach in sets. Ooh, all right. So why do waves tend to approach the beach in sets? Again, this whole question is 803, so I'm struggling here. I think the idea is that we have a dispersal. You know what? I don't know. let's check the answer here. The surface impression is accurate. Individual plane waves advance through the envelope of a wave packet quickly at the rate of the phase velocity, but then die down in amplitude as they approach the front of the envelope in order to maintain the envelope shape, which advances slowly at the rate of group velocity. Oh, right. Okay, so because, I'll write this down this way. Because approach wave packet. So let's draw a little picture of this guy right here. So we've got our surfer sitting on a surfboard, waiting for the waves to come in here. And what that person sees these waves approaching pretty quickly, so he's excited, but the actual group is moving kind of slowly. So when this wave gets to here, it mostly dies down. Okay. So definitely some gaps in knowledge there. All right. Let's try. Okay, good. Some equations I recognize. All right, let's try number 2. Let S be the number of spots shown by a 12-sided die thrown at random. Calculate the expected value of S. Calculate the standard deviation in S. Calculate this and this. Okay. So this is going to be equal to, so a 12-sided die is going to have these probabilities. You're going to have a probability of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So your expected value of this, because each of these are evenly probable, is going to be right in the middle. So it's going to be 6.5, right? This is just equal to, now there's some simple ways to calculate this. I don't really want to go through it all by hand. So is there any substitutions I can use from the notes we had? I can make this a little bit faster to calculate. Oops, this is from problem sets. Where did I write down? Okay, here we go. So this is it's going to be the expected value of a squared divided by the expected value squared. So this is going to be equal to s squared minus squared. So let's just go through all of it. So if we square all of these results, we have what? 1, 4, 9, 16, 25, 36, 7, 49, 64, 81, 100, 121, and 144. So what is the expected value now of these numbers? So let's add them all up. Get my calculator out. This is just addition, so this one should be okay to just do on my phone. Let's find the calculator. So we've got 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64 plus 81 plus 100 plus 21 plus 44 equals 650 divided by 12 possibilities, and we get equal to 54.16 repeating minus 6.5 times 6.5 is equal to 42.25. So we have 54.1666 minus 42.25. It's equal to 0.916 repeating. All right. So this should be right. And then if we had 2 dice, so 2 dice is going to be the sum of all these possibilities. Ooh, is there an easy way to calculate this that I'm not thinking of? Binomial, something like that. Where is it? Expected value is going to be maybe I'll just write it all on a line right here. It's a little annoying that these are 12-sided dice, but four. And how many ways do we have of getting each of these? One way of getting each of these. I think it's, what's the binomial formula? We've got 2 ways of getting these. Three. It's the let me grab a probability textbook and see if I can't find that. So I'm gonna make mistakes otherwise. All right. We now have again from my MIT Challenge Days Introduction to Probability, this textbook. So let me see if I have anything. Do I have an index here? Binomial 77. Sorry, not binomial. What's the right way to do this? So 1 we can't get. I don't know why I'm I'm writing it that way. Can't get 1 because it has to be 2. There's one way of getting 2, just one way of getting 24. 23 we can get with an 11 and a 12, or 12 and 11. So there's 2 ways of getting this. There's 2 ways of getting 3, 1 and 2. 4 we can get in how many ways? 4 we can get with a 1 plus a 3, 2 and 2, and 3 and 1. So this goes up to 3, this goes up to 3. 5 we can get in how many ways? We can get 1 and 4. We can get 4 and 1. We can get 2 and 3. We can get 3 and 2. And I don't think there's any other ways of getting it. Right? And then 6 is 3 and 3. Plus we have 2 and 4 times 2. And we have 1 and 5 times 2. So this is 5. I think this is the pattern. All right, so this is our these are our outcomes. And then to get the average, we just have to get the expected value of, I'm just going to call this 2s. Is going to be equal to, we have to multiply all of these out. Let's maybe do this in a Google Doc to save some time. Jeez. All right, let's type this in here. So we have let's drag this forward. And then this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And then we can get the expected value is equal to sum of this times this. Let's begin multiplication first. Equal to this times this. These. This is 13. I suppose we didn't really need to do that one, but we can do the squares now of these. So if we want to calculate, this, then we need to figure out 13 squared. So it's going to be something minus 13 squared. And what is the S is squared. So that's going to be expected value of S squared. So we want to multiply each of these by 2. Add a new column. So this is going to be equal to all right. And then it's going to be to this. So this. So this. So equals, this is wrong. Really? 13 squared. I'm making a mistake here. Oh, no. Oops. All right, let's add another column here. So this is the squared values times this. Let's add a new column here. So it's equal to this times this. Oh. It's equal to some this. These. 92. And then we have this minus 13 times the mean. And we have, this is 192.8 equal to 23.83 repeating. All right, well, hopefully I got this right because this is stuff that I've definitely studied before. So let's go over to the solution set. All right, let's use the pen here. So this is correct. Oh, should I have taken the square root of this? I think I should have taken the square root of this. Yeah, this is the variance. So let me just, I'll do it in the spreadsheet. That'll be a bit easier. So we've got equals square root 9166 and equals square root of this. So hold on a sec. The actual, this is actually not. This is 3.452, and this is actually 4.88882. Let's go back. $3.45, okay. Or Where's the next point? Oh, C, okay. All right, so I brute forced this, but what did they do here? Oh, interesting. Interesting. So this is S1 squared plus 2 S1 S2 and then this, I guess we can just take the expectations out because these are linear, so S1 squared plus minus. And because they're dependent, the joint probability of obtaining first and second times this, we have so that because they're independent, this is the same as this. So this cancels with this. And then we just have S1 squared plus S2 squared minus S1 squared plus S2 squared. But we know that S1 and S2 are the same, so this is 2 times. Oh, that's very interesting. See, that's a little cleverer than I would have gotten. All right. Let's go on to question 3. Dimensions of psi. What are the dimensions of psi? X, okay. so we know because the norm squared psi is a probability density, which is 1 over length, then this has 1 over root length dimensions. That's directly from the lecture. B, of the Fourier transform of psi. Oh, okay. What is this? Well, if we take the complex conjugate of this, should we not get the probability of finding a particular momentum? So this would be 1 over p. So that would lead this to be 1 over square root of p. 1 over square root of mass times length over time. So if they wanted in units, this would be 1 over square root of meters. And if this was in units, this would be 1 over square root of kg meters per second. Let's see if my intuition is right here. You start with Born interpretation, okay. All right. We have okay, so I'm using so I'm going to put a little note here. So K, this is the so this is not momentum, this is the probability of finding a certain wave number, which is equal to 2 pi over lambda. So which is order 1 over L, ergo root L. So I'm going to make a note to myself when using momentum, remember wave functions, not 1/2 mv squared. All right, let's do question number 4. Fourier transforms and expectation values. I think that was it. Was there any more? Yeah. Question 4. Fourier transforms and expectation values. In 804 conventions, a function f of x and its Fourier transforms f tilde k are related by this. Okay, that we know that. By definition, the expectation of x is equal to this, is equal to that. Using the definition of expectation values of powers of the momentum operator, the form of the momentum operator, this, and the definition of the Fourier transform show that, so show, what are we trying to show? Trying to show that is equal to dk norm squared hk all right. All right. Definition of expectation values. Of the momentum operator. So the momentum operator is equal to negative IH bar dx. This is the momentum operator. So show that the expectation value of this. Oh, so this is a given. Oh, okay. So we're not deriving that formula. This is a given. So we just have to use these formulas they've given us to get the other one. So let's just start with A. So this is going to be P hat to the 1 is equal to EK X compass conjugate X P hat. Oh, excuse me. X. So we can just insert that into there. And so what are we trying to get? Let's try to go up and solve something here. So what do we have right now? We have psi in the x domain. And what we want is psi, the Fourier transform of psi. So to get the Fourier transform of psi, let's just try substituting. Let's just start with something dumb and basics. This is not dk, this is dx. Yeah, x. So this is going to be of dx e to the negative I kx sine complex conjugate of x. And then we're going to have substitute this out. Times negative I h derivative with respect to x, integral with respect to x. Again, e to the negative I kx psi of x. So this is going to turn into sorry, I've made a huge mistake. What do I want to do here? No, this eraser is awful. I'm just going to use this one. All right, so I have to find the formulas for these. So these are in terms of x, so I need to do the other way around. So I'm doing it the wrong way here. dk e to the I kx psi tilde of k complex conjugate minus I h bar dx dk e to the I kx. I don't know whether this has got me any further. Josh was asking, what are the prereqs for being able to do this? So technically, you should have 801, which is classical mechanics, 802, which is electromagnetism, 803, which is waves. I don't have waves, which is why I'm struggling a little bit with some of these problem sets. You should also have 1801 single variable calculus, 1802 multivariable calculus, and 1803 differential equations, which I have done. But again, this is a long time ago. 8 years ago was the MIT challenge. So I'm also playing a little bit of catch up as well. So what do we have here? So I don't feel like that was the right way of doing this problem. So what's a better way of doing this problem? Momentum operator, form the momentum operator, definition of Fourier transform. So I know this intuitively, but I'm trying to figure out how to prove it with math. But basically, I need to show that what you should the expectation of taking the momentum observable corresponds to corresponds to the Fourier transform. Yeah, I prefer pencil and paper. All right. what needs to get inserted where so I can do this. Well, what do I know? I'm just going to write down some things I know so that are going to be tricks. So one thing I know is that because the momentum operator is taking a derivative, and because the Fourier transform is an integration, the momentum operator is going to cancel the integration, and we're going to end up with, that's how we're going to avoid that problem. So let's maybe start there. So if we take the momentum operator, oh, let's not do the expectation just yet. The momentum operator of psi of x, we're going to take essentially, because we can take, let's say we get psi of x is equal to 1 over root 2 pi I guess this is a definite, I'll put it there, dk e to the ikx psi tilde of k. If I take the momentum operator on each of these, but the momentum operator is differentiating with respect to x, so I'm not going to get what I want. So what if we try doing this? What if we do momentum operator on k, this equals over root 2 pi negative infinity dx. So this dx matches what we want, e to the negative ik x psi of x. So this is the thing that we have to cancel. So let's try taking the momentum operator of each of these. So that's going to be equal to momentum operator of psi tilde k is going to be equal to negative ih bar. I guess we'll just divide it by root 2 pi right here. And then we're going to have dx, and this is infinity, negative infinity dx. So this stuff's going to cancel, and we're going to get e to the negative ikx psi x. So what's going to happen next? Well, what do I need to have the formula in? What's the end result? Expectation. So let's just do, we need expectation in the norm squared of this h and k. So momentum hat times this is equal to this. Therefore, if I just, these are just some stuff. So if I move it around, we're going to get what? We're going to get so divide this out. We're going to get e to the ikx. We're going to get so the negative h bar is going to be on the bottom. So I could just do this quickly, but I want to make sure I don't screw up the math here. 2 pi over negative I h bar because this IH bar is, we can, sorry, we can multiply -1, we can factor out the -1 here. No. Let's write this down here. P hat psi tilde. Okay. But I kind of want if we're looking at the form of the thing, we want h and k to come down. And the only way the k is coming down is for taking the derivative of that. So maybe this is also not the right starting point. How can I get it into that format? Maybe I'll work from the equation that we are showing and go backwards. So I'm just going to leave this for right now because maybe this is the wrong direction. So if we go p hat is equal to this dk h bar k. So we split this up and we need momentum operator here. The momentum operator is acting on side x up there. How do I get this to work out? So what are our options? What can we do to get this into the right format? Well, we can take, so I've tried going from the expectation and I tried going from the Fourier transform, and then I'm now trying to go through from the equation we're showing, but I'm missing something. So we know we're going to want to cancel off this integral with the momentum operator. We also know that we're probably going to want to integrate this edikx because we're going to want to drop down the factor of k. Factor of minus ik is happening somewhere too. So we've got some pieces here, but we've got to just put them together. Essentially what I'm looking at here, I'll just do it on the page here, is that we know because there's this hk here that this k, which is only kind of naked in the formula in this exponential, is going to get this guy to plop it down. I'm also imagining this exponential is going to nuke this thing right here. So maybe it's the fact that we have two of these things where that's going to matter. So let's go from the expectation value of the momentum again. This is what we were trying to show, but let's just put that aside right now, and let's try to go to this formula just for the one-dimensional case. Dx psi is x. All right, and then let's pull this out. Negative IH bar dx. Right here. Now, this expression can be a set of, we can take the Fourier transform of that. But I don't know whether that does what we want, because then we have the integral in k. And this is derivative with respect to x. I think that's just going to lead to a mess. What if we do it on these tilde of x? We do it on this tilde of x. Well, I'm feeling kind of stuck. I feel like I should be able to do this, though. I feel like I'm missing something simple that is the key to bringing this all together. So I don't really want to look at the answers. But it's not popping into my head what I should be doing right now. So do we want to just leave this problem for a second and go on to number 5? I'm going to make a note here. I'm going to just leave this one for a moment because I need to get some fresh eyes on it. Sometimes this is a good way to handle problems. If you're struggling with something, just put it down, go work on something else. And then when you come back at it, you might, oh, right, I'm supposed to do this. Now, unless there's something complicated, I'm hoping this is not some integrating by parts or one of those things that I'm too rusty at to be able to apply to this. But I think there's something simple, and I'm just missing it right now. right, so I'm just going to leave some space here, and then let's leave a little gap, and then go on to number 5. The delta function. Okay, delta functions. The Dirac delta function, dx, defined by the condition. All right, well, we know that. Or more precisely, this. Okay. Oh, someone's asking me why I'm not checking the answer to the question. Well, because this question here, I felt like I should have the knowledge to answer this question, but it's not coming to mind. Now, I could check it, but the problem is that if I rush and check every problem right away, I'm not going to develop that real grit to handle these hard problems, because a lot of them, yeah, the pieces are there, but I got to be able to put them together. So what I have been doing is when I do the problems, I will, often if I get stuck, I'll check the first bit to get a bit of a hint and then try to go back, and then a little bit and go back. So feedback's important on the one hand, but you also want to have this kind of grit or kind of desirable difficulty to try to get the answer yourself. Because if you just see the answer, it's often obvious when you see it, but coming up with the answer yourself is much harder. So in this particular question I was working on 4, what my challenge right here is I'm stuck on this first one. And I know some pieces. I know, for instance, that we're taking the derivative. So we're taking the derivative. So with the momentum operator, that's going to kick down this k term, which we know is going to be here. We also know that there's going to be this derivative is going to have some ability to cancel the integral, which is also of x. But I'm struggling because when I'm trying to get the tildes to match, I'm dealing with k's in here and stuff. So I feel like this is probably, I'm on the right path, and I just need to find the piece of, oh, put this formula inside of that formula, and I haven't done that. And I'm a little bit fuzzy. I'm nearing the end of this studying session, so I just decided to leave it, because if I just go check this, I'm going to get the answer, but I'm not going to have necessarily striven for it the right way. So we're going to go into 5 and try 5, which is an unrelated question, so I don't think checking that answer is going to be important for this. So, Janelle's asking me, when do you take breaks and what do you do during those breaks? So I've been working 3-hour chunks right now, so I'm going to take a break in about 10 minutes from now. Well, I'm going to be doing some work during my break because I have a job to do as well. So lunch and work, and then I'm going to be back at 2 p.m. All right, Dirac delta function. Okay, so we know this, evaluate the integrals. This is some stuff with Dirac deltas. All right, let's just see if I can. So the way to understand the Dirac delta functions, if I can remember correctly, is that the Dirac delta function is basically, the Dirac delta function is essentially 1. So if you multiply, so if you take basically if you multiply the Dirac delta function with a function, it returns the value at that point. So it's kind of a magical function for this. So let's look at these ones here. So we have in this function, so let's write it out. Okay, from the interval of 1 to -3 of dx delta x plus 2 times x cubed minus 3x squared plus 2x minus 1. So this means that this is occurring at the -2, x equals -2. This is occurring. So basically, we just have to evaluate this at -2. So you have -2 cubed minus 3 minus 2 squared plus 2 minus 1. I believe this should be right. So let's just go over here. So this is going to be what? Negative 8. It's going to be minus 3 times 4. Let's change this to 12 minus 2 minus 1. So this should be minus 23. Unless I did something silly. Oh, so Ryan's asking, delta function is an infinitely narrow and infinitely high Gaussian. Yeah, that's one way of putting it. I mean, it's not even really a function, because if you integrated something that's just piecewise looks like this, you don't get these answers. So it's a kind of I don't want to say made up thing, because all math stuff is a made up thing, but it's not just a normal function. It's just defined to have these properties in the limit. So, all right, let's, oh, this is not B, this is just number 1. And number 2, x minus pi. So at pi, cosine of 3 times pi. So we want cosine of 3 pi plus 2. So 3 pi is negative 1 minus 2. This should be 1. Where are we here? Now this is minus 2. So this one's outside of the interval, right? So this one's going to be 0. It's a trick, because if we look here, this function only even exists between, or what this integral is only between here and here. So what we're doing is we're integrating over the multiplication of this region, but we got our little delta function sitting outside of that. So I think that's the trick for this question. So I'm going to skip ahead to question 5. Let's just try not to look at question 4. This is problem 6. Problem 5. Okay. Minus 25. Did I do my math wrong here? Minus 20, minus 23. What did I do wrong here? Plus 2x minus 1. Minus 2 cubed. 2 times 2 times 2 is minus 8. It's 3 times 4. Minus 12. Ooh. Yep. There we go. Forgot to multiply those two. Well, let me do that in pen so I know that I did make a mistake. I've been trying to be good about doing the answers from the book so that when I look back, I know what ones I got right. And then this is right, and this is right. Okay, so some stuff we're getting right. That's always good to know. All right, let's go forward to part B here. You know what? Before we go into part B, I'm gonna take a break. I'll just answer a few questions that have been coming up in the chat, and then I'm gonna take a little break, go for lunch, try to come back around 2 p.m. And we're how much more is there in problem set 2? Let me just check. This is the, so we have up to 8, and we're midway through question 5. So we're about halfway through problem set 2. And so I will answer a few questions here. So how do you, all right, what are some things here? What do you do during breaks? Oh, okay, let's go back to Joshua. I don't know whether Joshua's still here. This was asked a while ago, but are you going to get into doing AR machine learning? So I did do AI machine learning during the MIT challenge. Not a ton, though. A lot of those classes that were on the OpenCourseware were kind of before this deep learning revolution that has been happening recently. And I mean, the techniques existed, but there wasn't TensorFlow. There wasn't a lot of these commercial applications and all this impressive advancements due to incredible computing power. So I'd like to go and do more machine learning. I feel like I understand some of the basics of it, but that might be a separate project. All right, what else? Who else has asked me questions here? Spaced repetition with problem sets. Do you go over the problems that were difficult and fixed scheduler to keep them in long-term memory? Well, during this particular course, it's over 1 month, so I guess we could say kind of like a medium-term memory span here as opposed to like a lifelong retention plan. What I'm probably going to do is that the first problem set and this problem set have some shaky points for sure. So I think after I get done the first 5 problem sets, we're going to try to repair those weak points, maybe with the Feynman technique, maybe with a little bit more practice, we'll see. And then I'm definitely going to go back over all of this stuff before the final. So I don't have a particular review schedule in mind. I mean, a lot of the details are going to be practiced pretty extensively, but some of the stuff I'm only getting 1 or 2 coverage points. Won't answering questions distract you from studying? So I have been trying to focus on studying. I haven't always been good about answering questions that are happening in the chat right now. My approach is that I'm probably going to take little breaks between problems to just answer some questions, and otherwise I'm going to try to ignore the chat. I mean, yeah, you're right. It is distracting. If you were studying, I'd recommend not doing it live streamed. But I mean, part of the reason I'm doing this is because I wanted to do it live stream. If I wanted to just learn quantum physics on my own, it would certainly be a lot easier to not do it on camera. Do you ever struggle with motivation problems getting started studying? Or are you just used to it? Well, one of the things that's been helpful is I have a schedule. You know, I'm live streaming this right now, so I know that, okay, I'm starting at this point and I'm going till this point. So I don't know. For me, I like this. I mean, it's challenging. I'm definitely feeling on camera a little embarrassed, a little shy that, you know, I'm screwing up a lot of basic stuff live in front of everyone. When I was doing the MIT challenge, it was a little bit easier because it's like, all right, I'm making bad mistakes, but as long as I get the exam right, it's okay. But I am trying to showcase that. So I'm trying to show that this is hard for me. I'm making mistakes, and how am I getting past that? But I think that if we're talking about motivation to study, a lot of people's difficulties with motivation is they have some anxiety about getting the negative feedback. So I'm doing these problems right now and they're not easy for me, right? I'm screwing stuff up. There's some problems that we've covered, for instance, these ones right here, that I don't even know these formulas. So I'm just writing down this stuff here, and I don't know this. I don't know these things. And so I'm getting them wrong. And so that is something that requires a little bit of oomph to get over. And I think planning your attack plan so that you just attack it straight is usually the right way forward. Because once you get into that rhythm of getting the feedback, getting the negative feedback, oh man, I suck at this, but all right, let's work on it. Let's do some more problems. Let's go back. Let's, you know, practice the skills that you need. Let's break it down and work it through problems. That's how you're going to go through it. And that's how I'm going through it right now. I mean, we're only in day 4 morning. So we still got quite a bit of time left before my kind of self-imposed deadline at the end of the month. And so let's just try to use the time we have available. So I appreciate everyone who's been watching this. I don't know how this looks like to the average person. I imagine that for some people, this just looks like gibberish. I mean, if you are doing some, you know, if you're doing quantum mechanics and you haven't learned calculus, this is all just going to look like nonsense to you. Similarly, if you're a physics student and you're in your senior or your master's or whatever, then I'm struggling through some basic stuff and you're probably like, tisk, tisk, you should probably know this by now. So it really depends on what perspective you're taking, but I hope you can get kind of even if you don't know exactly what I'm doing right now, you get kind of an overall gestalt of what my process is, how long I'm taking on the questions, how I'm going through it. I'm trying to articulate my thought process. Jal is asking why no music? So there's 2 reasons for no music. Number 1, and I actually have an article that's going to be coming out on this soon. Music, particularly if it's has vocals, takes up some of your working memory capacity. So it will be harder to do these kinds of problems with music. Now, if I was feeling more confident with them, so that this was more of a review session where I'm doing it and it feels pretty easy, then I might do it with some music just because it would make it more fun. So I'm not saying I never went with music during the MIT challenge, but it was definitely not on the hard stuff, or I'm likely to do it on the hard stuff. Programming, I find I can do with music, especially if it's not too challenging. But this kind of stuff, I'm not getting it right. I'm at the limit of my capacity, so no music. Similarly, this is live stream. This is going on YouTube. If I'm playing music, I don't have the copyright to broadcast that kind of stuff. I'm going to have my channel taken down. So that's another reason to do that. The only drug I'm on right now is a single shot of espresso in this morning in my coffee. So I'm not taking anything else. I don't really recommend it. I mean, I think a lot of these study drugs are just to help you focus. I mean, I haven't had much problem focusing over the last 3 hours. So maybe for other people who struggle with focusing more, they might want to look into nootropics or things like that. But I don't think these things really make you any smarter. They just let you focus for a couple hours, which is what we have been doing. So, I mean, let's sort of take a break right now. I'm going to be back in the afternoon. We're going through the problem set slower than I had hoped. I was hoping that it was going to be a bit easier, and I was going to be, on problem set 3 or 4 by now, so that we'd have more time for refinement techniques. This may change my schedule. My original schedule was, okay, I've got all of April to work on this. I was hoping to get all the lectures done by the 15th, and then I could just use the rest of the time to dig deeper. Looks like I'm going to have to be pulling that in a little bit early. Now, I mean, the problem sets are usually they're usually harder than what's on the test, because the expectation is you're looking things up, you've got the textbook with you, so there's a lot of things here that involve numerical constants, tricky calculations, this kind of things. But I mean, it's still on the same order of magnitude. We're not really talking about something very different. And there's definite gaps in my understanding here. There's weaknesses on a calculation level. So this last problem, number 4, is not a conceptual problem. I definitely understand why this should be true. I just can't make the math work out. And I think that is my relative rustiness with doing calculus, which basically I haven't done since, about 8 years ago. And whereas other things are conceptual. So some of this wave function, this wave stuff, I didn't do waves, so I'm missing that. Some of the diffraction things, I think that was also in waves. A lot of conceptual things there. And then not to mention some stuff from the class involving the partial differential equations and whatnot that I'm not understanding. So I have to kind of make a decision about whether I want to dig deeper on any of these points right now. I think I'm going to stick to the plan of at least getting to problem set 5. So that might take me even past Friday, depending on how hard it is. But let's stick to this right now. I don't think that there's a better use of the time at the moment. Struggling through these problems is probably the best thing I can be doing right now. So I'm just going to keep working on that. And then, who knows, if I find the other problem sets a little easier, or they're a little shorter, or I'm getting through them a little faster, we might have some time to do some Feynman techniques and some other things after. One final question from Jill. Do you like to use Google if you don't understand why you make a mistake? Well, yeah, sure. Unfortunately, I mean, these are pretty specific questions that have pretty specific answers. So I don't think that this is like a generic question for Google right now. I mean, Google can kind of help if you need an extra explanation for a broad concept. But like, if I don't understand why this was 25, like the only thing I can do is go back to this exact math and work through it step by step. And then we found out, oh, I put 2 times -2 as 2 here in my arithmetic, and that's why I got the wrong answer. So, I mean, you got to kind of work with the material you're given. I've been using a few sources to jump to things. So I have this nice textbook, Ohanian Physics. You can really use any physics textbook. This is not one for the class. I haven't really done much in this yet, but this is the one I bought for this class, French and Taylor, An Introduction to Quantum Physics. And I also have a bunch of textbooks that I had from the MIT challenge. So I was popping open a Introduction to Probability textbook. I didn't really use it though. I mean, you can Google a lot of these things. So when I was looking for constants, I was Googling them. You can Google a lot of stuff like that. But the main material, the core material, is the stuff that's on MIT's OpenCourseWare. For a class like this, it's pretty thorough. All right. So it is now 11:07. I've gone a little bit over what I expected, but it's good to talk to you guys. I want to try to, the whole point of me doing this, beyond just my own interest in learning quantum physics, was that I wanted to live stream a project. I wanted to show my process as it actually goes on, rather than just talking about it in retrospect. So I hope that it's somewhat useful or interesting. Well, I guess we're just gonna have to see after this project's done whether this is something that's actually people can use as a little bit as a template, or at least a kind of a reference point for how to do it. So thank you so much for following. I'm going to be back on at 2 p.m. Pacific time.